Okay, Lucas, we can see your slides, so I think you are ready to roll.
All right. So I appreciate the opportunity to visit with you this afternoon, and this talk kind of picks up where, if you've been to any of our other soil fertility programming this winter, where we've talked about the economic implications of where we're at and how to bring that into consideration, to kind of leave off with, okay, how do we take these economics, some of these decisions we're making on the field scale, and how does that fit into a site-specific management type framework? So gathered some thoughts on that this afternoon. This isn't all inclusive, but we'll hopefully again give some ideas and concepts. So that's what we're going to talk about, some site-specific management opportunities. I know this isn't quite as handy as an in-person deal, but please, if you guys got questions or comments, even though we're on virtual here, would much rather have you guys ask those as we're going, and the other folks help moderate will flag me down if I don't see something come in on the chat window. So you guys have probably seen these slides already this fall or over the winter, and no surprise to any of you in terms of where we're at. If we think about from a long-term perspective, one of the ways we can kind of put things into perspective is think about price ratio. This happens to be how many pounds of corn does it take to buy a pound of P, or how many pounds of corn to take to buy a pound of N. This data is only up through November, and certainly we've seen things continue to strengthen a little bit since then. And so we're really about into where we were here towards the end of 2008 in terms of peaking out that price ratio in terms of how expensive nitrogen is relative to the crops that we're growing. We're starting to see a little bit of easing in urea prices at the Gulf, but it's going to take a long time, take some time anyways, for that to work its way through the system to where we see those reflected at the retail levels. So actually on agmanager.info, Greg Eibendal had just put an article out on that not too long ago discussing some of the potential price movements. But we've got that happening at the same time. We've got some sanctions, tariffs put into, not sanctions, but tariffs put into place on UAN, which affects imports coming out of Russia. And so a lot of moving pieces here. Similar thing on wheat, and I'm going to talk, most of my talks, we'll talk some about nitrogen, but we'll have a heavy emphasis on managing phosphorus from a site-specific standpoint. One thing I want to point out on both these graphs, maybe a little easier to see if we come back to the corn graph here. If you note the solid line, this is our price ratio on corn to phosphorus. And the one thing, going back to the fall of 2019, we were doing some soil fertility schools, and I remember pointing out, if you look back here, really the fall of 2019 was a historically cheap time to buy phosphorus relative to the value of the crops that we were raising. And so on owned ground or long-term rented ground here in the fall of 2019, there was really an opportunity to do some building of soil test P levels. And folks that did that, find themselves in a very different situation today. They have a lot more flexibility to cut back or even completely skip phosphorus applications here at 80, 85 cents per pound phos, if you took advantage of some building opportunities there. So, we saw that in late 2019. We saw that again here in 2012 to 2013. Of course, after the 2012 drought, we didn't have a lot of extra money to spend. But I guess my point is this historical data, I think, can be useful in identifying those buying opportunities for things like phosphorus, or if any of you further east are dealing with potassium, those things that we can treat as more of a long-term investment in the land. I think these long-term data sets can help us find some of these buying opportunities. Okay, so I'm a pretty firm believer that anything we think about doing from a variable rate standpoint, I think soil test data needs to be a pretty strong piece of that. And so, over the years, and again, especially here this fall and winter, we've talked about that, the whole economics of soil testing. And really, in even average years, we can show pretty significant economic returns to making that soil testing investment. But certainly when we think about where we're at price-wise today, that becomes even more important, not only because of high fertility prices, but also high crop prices. And so if we think about this double-edged sword of, we certainly don't want to be short on crop nutrients because that's going to result in a yield hit, nor do we want to over apply, expensive inputs. And so this is kind of just looking at where we're at here, kind of an updated look on the value of soil test information. This happens to be looking at soil test nitrogen, okay, and using some current values in here. So what I'm saying is, if I know nothing about a field, if I don't do any soil testing, what assumptions am I going to use to make a decision with? And in this particular example on soil test nitrogen, we're saying, okay, if I know nothing, I don't pull any profile N samples, I'm going to guess that I have 40 pounds of profile N out there. Okay. And so what we're looking at is, what's the cost of being wrong? How much money do I leave on the table if I'm wrong? And so here's my other assumptions. I've got corn at 5 1/4, wheat at 7.46, dollar in, 65 cent P. This is a little bit light on the phosphorus side on price right now. My yield goals are 95 bushel corn, 60 bushel wheat. Okay, it's kind of a Northwest Kansas dryland example here. And this is looking at just the nitrogen piece. So if I've got 40 pounds in the profile, and I guess 40, hey, good for me. I'm a good guesser. I didn't leave any money on the table. Okay. Now, if I start to back away from that and say, okay, I thought I had 40 pounds on the profile, but I really only have 20. Now I'm talking about leaving, $3.50 an acre on the table. If my profile was empty, now I'm talking about leaving somewhere in the neighborhood of 13 to 14 bucks an acre. Okay, this is yield loss. We're leaving yield revenue on the table. If we go the other direction, and I think I have 40 in the profile, but I really only have 60, or I really have 80, now I'm talking about, I'm not utilizing that nitrogen that's already in the profile. I'm going to over apply in, and so that causes an economic loss as well. Interestingly, where this actually becomes a bigger issue is on the phosphorus side of things. And so here we're thinking about, if I know nothing, I'm going to guess that I've got 16 part per million out there. Okay. All the other assumptions are still the same. Okay. But if I think I have 16 part per million and I really have 11, now I'm talking about leaving $3 to $4 an acre on the table. And this is where it really starts to get pretty steep is, okay, what if that field's really 6 part per million soil test P? Now I'm talking about leaving, somewhere in the neighborhood of 14.5 to over $16 an acre per crop per year. So this is annualized, assuming we're in a 3-year wheat corn fallow rotation, but this becomes an annualized type loss. Okay, now, in all fairness, this is probably a pretty extreme example, right? We're probably going to know if we've got a whole field that's testing as low as 6 part per million. We're gonna have a pretty good idea that we've got some deficiency out there. But where this comes into play is from from a site-specific management standpoint is, I'm gonna have a field that test average, the average soil test value of that field, or if I go do a field level composite, comes back at 16 part per million. But what about those areas out in the field? What if I've got some areas out in the field that are 6 part per million? And now I've got, this starts to justify some economics for variable rate management. And that's what we'll spend just a little bit more time discussing. Now, everything I've just showed was based on the assumption of perfect soil test values, soil test information. Now, is soil test information perfect? Is soil sampling perfect? Well, I think we all recognize the answer to that is no. There's always some inherent error in there. But how do we get as good a quality of data to make a decision with as possible? Because the higher quality data that we're using, the better job we're going to do of capturing those economic returns that are out there available to us. Okay, and so how do we get at that? So good decisions require good data, and really ultimately good data comes from good procedures in the field. And I'm going to talk a lot about number of cores, but equally important than that, or even more important to that in some situations, is core depth, consistency and depth of sampling. So again, if you're using K-State recommendations, or certainly in general, our recommendation is that for things like soil pH, Now there's some exceptions to that if we're in no-till, but for organic matter, for phosphorus, for iron, zinc, for most of the things we're looking at in a soil test, we're wanting a 6-inch sample. The consistency in that depth is really important, especially as we think about long-term no-till, where we know we've got stratification happening. We see stratification in pH. We see stratification in soil test P, and so that's where this consistency of depth becomes even more important, because if we shallow a sample a little bit, that's going to tend to lower our pH values. It's going to tend to increase our soil test phos values, and if we overshoot the depth, that will have just the opposite effect. That will tend to result in higher soil pH values and lower soil test phosphorus values. And so consistency in depth is becoming even more important. For those of you that might be looking at changes in pH over time, I know in north central Kansas, Smith, Osborne counties, we're seeing more of this, where we've got lower soil pHs coming back. We've given some guidance there. Sometimes it's useful to go in and sample a 6-inch sample, but also 0 to 3 as well. And while we're on this topic of pH, and unfortunately I didn't include that in my other slides here on variable rate, but I think the one thing to keep in mind is, when it comes to liming, that truly is a no-brainer circumstance of where variable rate has a high economic return on investment, really much larger than the nitrogen or phos or really anything else we can do. So if you're in that situation where you're considering doing some liming, I would absolutely recommend a grid sampling, and oftentimes we can justify economically, the industry standard. There's really not a lot of science to this, but we've kind of settled on this 2.5 acre grid. But a lot of times in our variable rate pH work, the economics would actually justify a higher intensity, a smaller grid size than that standard 2.5 acre grid. Or there's other technologies out there. There's the Veris sensor platform that not only has EC but has pH as part of that as well. And so we've got service providers in the state that will run those and give you a really high density sampling of soil pH, and we've illustrated pretty good economic returns to that as well. There's things you got to be important. You got to recognize, making sure that we're getting good calibration data for the high and low soil test areas in the field to match with those sensor readings, but a good technology to consider. But in general, if you're thinking about liming, I really think variable rate is the way to go. Okay, so thinking about a number of cores to make a good sample. And it's important to recognize, that soils vary in very short distances. Oftentimes this has been discussed. There's some papers where they've actually went out. The Oklahoma State guys referenced some work that they've done a lot in some grass. I believe it was brome. Maybe they went out and sampled on a 1-foot grid, and just showed what the high level of variability was sample to sample. Okay. Now, some people have actually taken that data and used it as an argument to say, well, soil testing is of no value because it's too variable. We've got to find other ways to do variable rate. Well, I think if you keep in mind the fact that they were doing this in a 100 by 100 foot area, and it's like, okay, well, what was your goal? Was it to properly describe this 100-foot square area, or was you actually trying to get at every foot? And I think what that data really illustrates is we have a high degree of small scale variability across the soil landscape. We got variability in the parent material of the soil, erosion, how it was deposited. But I think what I'm probably a little more concerned about, so we know that high level variability is already there, but then what becomes even the larger concern is, think about the man-made variability that we put onto the soil through our management in a lot of our croplands. Okay. Are we band applying any of our nutrients? Okay. Are we grazing? Are we running cows on the stalks? Let's think about those things that we introduce from a management standpoint that are certainly creating a high degree of small scale spatial variability. So if we think about, last year, if we put a pretty good chunk of phos on and we band applied that phosphorus, and now we want to go out and we want to collect a sample now that is representative. If we think about what's our goal with the soil sample, okay, hopefully we're characterizing the soil volume, that's going to be explored by the majority of the roots for nutrient uptake. So if we go out and we pull a sample and we're going to pull 5 cores and then combine them and send that off to the lab. If one of those 5 cores is hitting where that phosphorus band was last year, what's that going to do to our lab test result? Okay, we know we're going to skew that pretty hard if 1 out of the 5 hits that old band. But if we're pulling 15, 16, 18 cores and 2 or 3 or 4 of those hit that old band, we're getting a fair representation of what those roots are going to intercept. Okay. And so, that's really, if we think about how do we overcome the small scale variability, it's more cores per sample. And I'm sure some of you have seen me show this slide before, but I think this is critically important to think about. And so we're looking at is, okay, for the number of cores, and this is a phosphorus example, for the number of cores that are going into that sample, what is the confidence interval around that average soil test value we get back from the lab? And so if we've got a 5-core sample, we throw that in the bag, we send it down to Manhattan to the lab. Okay, soil test lab sends you back a report and says it's 19 part per million. Now, what the lab, what it doesn't matter if it's K-State or Cervatec or American, whoever, no lab knows how many cores you put in the bag. And so all they can send back to you is this lab value. Okay, what you don't have as part of that is what's the confidence interval around that. Okay, if you look at plus or minus this 5-core sample, it's plus or minus 6 part per million. Okay, and so that's 19 plus 6. Well, that means it could be 25 part per million. Okay, it also means 19 minus 6, it could be 13 part per million. Well, 13 part per million, that's getting fairly low. I should be thinking about how do I get on some band application of phosphorus. Now, and at 25, well, that's high enough. Hey, we actually don't have to apply any if we don't want to. Okay, so a wide range of management alternatives just based on the potential confidence interval around this number. Well, what's the only way to get that down? It's to pull additional cores. Okay, and now the one thing you'll notice is the confidence interval never drops to 0. Okay, we could pull an infinite number of cores and we're still going to be plus or minus 2 part per million. That's just the inherent noise, the inherent variability in the lab analysis piece of this. But if we look at where it starts to flatten out at, think about this in terms of if you flip this the other way and think about it in terms of kind of diminishing returns, once we get here to about 15 cores is where this thing really starts to flatten out. And so that comes back to this recommendation of, we really need 15 or 16 cores in that sample to get a fair, to optimize the value of that soil testing information. In the early days of grid sampling, there was an argument of, well, being we're grid sampling, we're taking so many more samples, we can get by with fewer cores per bag. Well, that's true if you're interested in the field average. Okay, you're going to have a much better estimate of field average from grid sampling, even if you're only taking 5 cores per sample. But if I'm paying for grid sampling, I really don't care about field average. I want a good estimation of soil test phosphorus in each one of these grids across the field. Or if you're zone sampling, same thing. I really don't care about field average. I want a good estimate of my soil test phos level in each one of those zones. And so it still comes back to, and being this is overcoming spatial variability of small scale, this relationship holds true whether we're taking a composite sample for a quarter section or whether we're taking a 1 acre grid sample. It still holds true that we need 15 to 16 cores in order to minimize the error, in order to bring down this confidence interval as much as reasonably possible. And so there's an economic value to that too. If we think about the economics of, grid sampling, for example, okay, the lab fee that we get charged for that bag is the same, regardless whether there's 5 cores in it or 15. Okay, our fixed cost of getting a person, a truck, and a 4-wheeler to the field is the same, whether we're pulling 5 core samples or 15 core samples. What it really comes down to is what's the marginal cost of someone's time to pull an extra 5 cores. Okay. And so we've actually done the economics of this. We've talked to consultants. We've done stopwatch trials. We've said, okay, how long does it take to pull that 5 cores? What's the value of that person's time doing it? And interestingly, it basically comes out to about that 15, 16 cores again, is where that economic optimum is. And so here's one way of looking at that. If you think back to those slides I showed earlier in terms of the potential, economic returns to having good soil test information, how much of that was assuming we had perfect data being fed in. Now, how much of that idealized economic return do we give up? Okay, by feeding poor quality data into our decision-making process. So if I'm feeding in data that's based on 5 core samples, I'm going to be right less often. Okay, I'm not going to hit the mark. I'm going to be further away from where I need to be. I'm not going to hit it as often. So I give up some of that idealized economic return. Okay, and I'm giving up about $1.70 to $2 an acre. If I get down to if I take a 10 core sample, well, now I'm closer to right more often. And so now I'm only giving up about, 60 to 80 cents of that idealized return. And by the time I'm to a 15 core sample, now I'm only giving up about 48 cents of that idealized economic return. And somewhere between 15 and 20 cores is where the added labor cost no longer covers the improved return on investment of soil sampling. Okay, I see we got a question that came in the chat. Yeah, this is a really good question that comes, kind of comes back to this piece a little bit. But the question is, should larger fields, say 150 acres, be sampled as 2 fields or 3 to improve reliability? And, I think we see that vary a lot across the state. And I know, like I think NRCS, or I know University of Nebraska, they give some pretty blanket things like there should always be a sample should never represent more than 40 acres or blah, blah, blah. When I think about a lot of our fields here in Western Kansas, if we're thinking about field composite sampling, if I've got an entire quarter section that's mapped as Ulysses silt loam and there's really no topography, I have a hard time telling someone they should break that into 40s just because. Now, if there's good reasons to break a field up, if we know there's differences in past management history, maybe this portion of the field was broke out from sod 20 years later, or if we know we've got known differences in soil texture, we've got a sand lens that runs through it, or we've got some very pronounced clay side hills. I think if there's a good reason to break that up, if your goal is to do composite sampling, if you've got good reason to break that up, I think that's fine. But I, just to arbitrarily break it up, I'm not sure we capture a lot of good value out of that unless we're going to go all the way to some type of zone or grid sampling. But good question. But yeah, just to emphasize though, this relationship holds true whether we're pulling a quarter section composite or a 1 acre grid, or if we're doing something in between. Say you've got an 80 that has some different history in it. The bottom 30 acres was broken out from grass later, and we're going to sample it as this 50 acres and this 30 acres. This relationship holds true really for any reasonable size of land that we're trying to represent with a sample. Good question. Okay, evaluating soils data. Often these first pass evaluations are useful. What I think is always a good first step when you get soil sample data back, like grid sample data, is to look at the range, look at the histogram. Can we determine it? Not every field is a good candidate for variable rate. Maybe we can do some targeted sampling. Maybe we think we have a good idea where the high and low soil test levels are. We can sample those and then decide, okay, is this field a candidate for more intensive sampling? And it can give some indications of what maybe our immediate management needs are. Maybe, we're not going to do VRT right away in this first year. Maybe we've got a field that's not a good candidate. Its range of soil test phos levels are from 8 to 15. It just needs some pretty healthy blanket rates of phos put on. So we can make some of those types of decisions. So it's always good to plot a histogram of the data, see how it's spread out, look at the mean, look at the median. How skewed is it? Is the field fairly uniform, or do we have, just some very low soil test level areas, and then it's really, the rest of it is fairly evenly distributed? Just get a feel for what that is across field. I think this is some of the most useful thing you can do when you get soil test data back in. Okay, so we got a question. A field with 3 terraces. If you think of those 3 terraces as different elevations, if you sample on those elevations, how would that compare to recommendations from 2.5 acre grids? That's a good question, and that's the problem. The challenge is, without actually doing the grid sampling, we really don't know how that would compare. And again, it goes back to probably how uniform that ground would be within each of those three terraces. So one approach would be to take and sample those as 3 different zones and get a feel for what that variability there is. This is also where, if you have historical yield data, I think that can be a very useful layer in deciding, okay, what is the scale of variability do I have in the field? If I break this field into these 3 zones, does that match up pretty well with my yield data? Or if I look within each of those 3 zones or 3 terraces, if I still have a high degree of variability when I look at my yield data or bare soil imagery or past satellite imagery, any of those things that might give us some indications as to differences in productivity, if I still have variability within those zones, then it may be a candidate to sample that a little bit deeper. If we go back to any type of grid or zone management, or if we think about zones, for a zone to be successful, it needs to be homogeneous. Our idea is to create these zones that are more alike within themselves, that are less variable than what the whole field is, to identify these areas that are similar. If you have a zone that still has a high degree of variability within it, that's not a very effective zone. We've not met the mark for what we were trying to do there. Okay, so let's think about this a little bit. What distribution of soil test values would make the best candidate for variable rate? Okay, assuming our critical soil test P level is about 20. If we think about a field that has a mean of 28, or a mean of 18, or a mean of 10, if we assume that these things are going to be somewhat normally distributed, if we've got an average of 28, that's a pretty good indication that a pretty good chunk of that field is going to be above our threshold P value. If we've got a field average of 10, that's a pretty good indication that the bulk of this field is in need of a pretty healthy application of phos. But if we think about, if our average is right around that critical soil test P value, that most likely is the field that's going to have the greatest economic return from variable rate phos. Okay, so here's a couple fields as an example. If we look at here, this field, we've got an average of 11.5 soil test P. The range is from 4 to 21. Okay, so our average P recommendation on that field would be 35 pounds per acre. If we did that, or the other thing to look at here is we've got 4% of the field is above 20 part per million. So only 4% of the field actually calls for no phos. 96% of the field is below 20 part per million. Okay. This is telling us that really, if you go back and look at the mean here, this field just overall needs a pretty healthy dose of phos. Now, if we look at field 2, we've got an average around 31 part per million. The range is from 16 to 62. About 90% of this field's above 20 part per million. Okay. Doesn't really call for phos. Only 10% of the field is going to call for phos. So really 2 different extremes here in terms of neither one of these are really a great applicant for variable rate. This one needs basically blanket rate across, the majority of the field, whereas here the majority in field 2, the majority of the field, we don't actually have to apply anything if we don't want to. But it's important to recognize what percentages of those fields would result in over or under application if we did do blanket rate across it. When we think about developing variable rate application maps, we're just basically trying to make input decisions on a smaller scale. And so, a couple ways that we can implement things that we do at a larger scale, rate-based equations or decision-based, or a couple different ways we can think about developing variable rate application. So just a very typical example would be using our nitrogen rate equation. Okay, or we put in, maybe we develop a yield goal layer for that field. And we use yield goal, maybe we have grid sampled soil organic matter values. And so we use that to drive a variable rate equation across the field. Mathematical equations, there's some advantages. They're easy to update. They're dynamic as our input variables change. We can mix different types of information together. So soil types and soil test levels. The challenges are they got to be developed. It takes some time to actually think through this process, and we'll give an example of that here in a little bit. We can also have just kind of some very binary decision-based variable rate applications. And so the most simplistic version of this would be, a seeding rate script for irrigated versus dry land, okay, underneath a pivot versus the rest of the field. Or if we think about back to phosphorus, maybe I'm going to make a starter application decision, either rate or starter on off, based upon the soil test P level in the field. So here's an example of, we've got soil test P levels in the left-hand pane here that have been interpolated, and basically using a rule of somewhere around 25 part per million. I'm saying anything over 25 part per million is getting starter P. Anything over 25 part per million is not getting starter P. Anything under 25 part per million is. And so making some of those decision-based type rules based on soil test values. One example. Okay, so thinking through this, and this goes a little bit into that question earlier about the economics of grid sampling. Now, the problem is to truly evaluate the economics of it versus zone or field composite. We have to spend the money on the grid sampling to actually see what we have out there. But I've got a couple fields I've run some examples on. These aren't the best. I'm still looking for the perfect field to illustrate this with. You'll see why there's some challenges in the fields that I've picked. This first one, this is a field in Thomas County. The producer sampled it on 2.5 acre grids. He did 15 cores. We're estimating we've got a confidence interval of about 3.5 part per million on there. Here's the satellite or the aerial imagery you can see where the sample points were. If we look at the histogram of that data, there's something that should stand out to you here. If we look at the average, is 21.7 part per million. That's right at our threshold value. But look at this, we've got a max of 217. And if we look at the histogram of the data, we can see that laying out here in this one sample that's even above 200 part per million. We do have a few spots in the field that are fairly high soil test P, okay, 45, 60, 65. The bulk of the field, is really in this 15 to 20 range, with a few more in the 25 to 30, and we've got a few under 10. But this 217 should stick out to you. And when we run the math, run the interpolation on it, this is not a good example of interpolation. Anytime you have these really distinct bullseye type patterns, that's a sign that whoever ran the interpolation had the power set a little too high. So you're giving a little too much weight to the sample that's right close in that area. But this 217 shows up, and it's not uncommon for us to see these sorts of things. Typically we see those being old farmsteads, old feedlot areas. This happens to be a little more modern cause, and that is when the cows are out on stocks. Where do you think the tanks are at? Water tanks are at. And so, it's one of those things, we think about, and then you kind of go through, okay, how do I actually want to manage this? Do I want to delete that, ignore it, treat that as field average or the data around it? Or, most of the time, these are areas that are small enough we're probably not going to do a real effective job of targeting them differently with our application equipment. So maybe more prudent to treat it just as kind of as field average or as the average of the values around that, just throw out this high value. But anyways, if we look across this field, from the areas of higher to low soil test P, what we can do is we can go and run the economics at each point in the field and say, okay, what would have happened if we had done a blanket application versus what if we had done variable rate based upon this grid sample? And so here's one way of looking at that. So here's the change in gross returns from field composite management versus variable rate across the range of soil test P levels that we saw in this field. Okay. Now, keep in mind, our field average is right around 20 part per million. So if we were making a decision based on that composite sample, basically our recommendation would have been essentially nothing, or maybe only starter only. Okay. But a very small application. So as a result of that, we're not overplying a lot in these areas that are above 20 part per million because just of how our field composite decision would have been made. But this is the point I was making earlier. We get into the few areas of the field that are low soil test P, the differences in gross revenue can become quite substantial. And this is really what is going to drive for a lot of fields, for fields where if your field mean is coming out at 20 part per million or higher, so you're basically not really going to over apply a lot, the economics are going to be driven by how big are the low soil testing areas in the field. That's really is what's going to drive the potential ROI from variable rate management. And if we look at, we've done some previous analysis with this field using long-term average returns to variable rate, long-term prices. So I was like 350 corn, 475 wheat, 33 cent in, 50 cent or 45 cent FOS. We were getting returns in the neighborhood of 381 per acre on wheat and 449 per acre on corn. Now, if we stick today's prices in, 5 1/4 corn, 679 wheat, $1 in, 85 cent FOS, you can see here now in these low soil testing areas, we're talking about average returns to variable rate on the order of 546 to 678 per acre per crop per year. Again, this is in the context of a wheat corn fallow type rotation. So it really boosted our improvements in gross returns in these low soil test P areas, looking at variable rate compared to field composite management. Means we were putting on some low level of FOS. It also increased our gross returns up here in these higher soil test P areas as well. This is really driven by the higher FOS price. The fact that we're looking at 45 cent FOS versus 80 or 85 cent FOS is what's really driving this overall improvement in returns to variable rate at the higher soil test P levels. This is being driven by higher crop prices down here in the low soil test P levels. This is being driven by the fact that grain's worth a lot right now. And so the penalty of leaving yield on the table in those low soil test P areas is quite large. Okay, here's a field that's another example, a little more spread out in terms of the range. And so if you look at this field and we do the interpolation on, this is on a little bit tighter grid. This is on like I think about a 1 3/4 acre grid, just because we knew we had a higher degree of variability in this field. Again, always good to go through and look at if we look on the summary table here on FOS, minimum of 10, a maximum of 78 part per million with an average of 29. So from a field composite, if we had done a good job of taking a field composite sample, we would hope that number would come back around 29 part per million. And basically, we would say don't put anything on. Okay, that would be our recommendation. But we know, if we look especially over here in the southwestern portion of the field, in this little neck that comes up here, we got a fair bit of acres that are 12, 14, 10 part per million. We've got some other stuff here in the northern part of the field that's a little bit closer to that threshold value. Most of our high soil testing P ground is here along this southeastern portion of the field. So we've got some pretty defined spatial structure there. Again, applying, if we go through and look at the economics at each one of those portions in the field, and this is where some of this low soil test P stuff, And again, what this also plays in, thinking back to if we were doing a composite, we'd be putting on 0 phos. And so we would really be hurting ourselves yield wise in these low soil test P areas of the field. And so even under long-term average prices, we're talking about differences in gross returns in the neighborhood of 38 to almost $50 an acre. And when you put today's prices on it, we're talking about 57 on up to $70 an acre. Now, again, this is really being driven by yield loss, by revenue loss, predominantly really in this area of the field, kind of in this southwestern portion of the field. Along with, we've got some other areas, 15 part per million up here, 16 part per million. These areas also, we'd be giving up some yield revenue if we were doing phos management just based on a field composite sample. So again, but always useful to go back and look at the ranges and histograms. Here's a field that's an example of, not a great candidate for variable rate. Now we grid sampled the whole thing to figure it out. But if you look at soil test phos, we got a minimum of 20 and a max of 67, an average of 38. So we could do some variable rate and intentionally pull down some of these high soil testing areas. But by and large, where a lot of the economics right now is being driven by leaving yield on the table with high crop prices in low soil test P areas. Really we're not going to see a lot of huge economic opportunities in this field here with a range of 20 to 67 in soil test P. Even with a soil test P average of 38, where our recommendation would be to apply nothing, we will have to watch these low soil testing areas, the stuff that's at 20, that's right at threshold. We don't want to mine those areas too deeply. Just another example of a field where, again, we've got soil test P. Now, this one's a little more interesting. We've got a range of 13 to 95. Okay, so if we look at those areas, here's that 13 here in this area of the field, but that's really the only thing that's very far below threshold. And so, again, another one of those fields that could benefit from variable rate, but probably not as good of an example as the first two. And if I think about the ideal example, I actually looked through a lot of fields and could not find the ideal example. But if we had something that was right around that soil test P average, right around 18 part per million, where we've got large areas of the field that are down in that 12, 13, 14, but we've also got areas of the field that are up around 30. That would be a situation that would be our highest economic return. How do we stretch the value of intensive sampling? And this is something we've talked about a lot over the years, but I think one thing that's a potential approach is you grid sample a field once, you establish some benchmark locations in there that you're going to go back and resample, and then kind of use a checkbook approach over time. If you've got yield monitor data, we can do a pretty decent job of estimating crop removal. And so we just kind of do that checkbook method of removal and additions at every portion in the field through time. This is an older example we'd put together of a field looking at yield monitor data to look at 4 years of removal. It took 4 years of yield monitor data, 4 different crops. If you add that together, you see in this particular field, we've got areas that are removing, the yellows and reds are 85 to 130 pounds of phos removed, while the blues are only removing, 15 to 45 or 15 to 65 pounds of P. Okay. And so we know we have, being able to keep track of that and basically do that checkbook accounting essentially for every spot in the field. I'm going to skip through this. So idea would be to establish some benchmark points. Some of those, we grid sample it. We take some of those highest soil test P levels, some of the lowest, some in the middle, and then we revisit them over time to make sure our checkbook math is on track and save us the expense of regridding the entire field. And that way we can stretch that value, improve the return on investment for that initial grid sampling that we do. Okay, most of this we have covered. We're going to hit on variable rate nitrogen just for a little bit. This has been fairly phos heavy so far. There's a couple ways of looking at variable rate nitrogen. So one way is to basically apply spatial data to our more traditional mechanistic nitrogen recommendations. And I'll give an example of that. And then the second thing that we're hearing, a lot about is sensor-based type approaches. And so we'll visit about that briefly and think about what are some of the benefits and limitations of that type of system. So the one thing I would say, if you're grid sampling anything fresh this year, where you've got weed out, even though we always encourage you to take a profile sample for nitrate, if you do have nitrate data from that top 6 inches, there's no reason not to use that data as part of a variable rate approach. We still want to account for, there's going to be some additional nitrogen in the 6 to 24 inches, but we know we've got variability, at least in nitrate in the top 6. So if you do have that data available from a recent grid sampling, no reason not to incorporate that into a variable rate approach, along with you would have organic matter data from that 0 to 6. And so we could use that to adjust the mineralization piece of that nitrogen recommendation. So this is just an example here of one field where we've done exactly that. We'd grid sampled this field actually right before it had went to wheat. And so we had that 0 to 6 organic matter and nitrate data, and use that along with some assumptions for that 6 to 24 inch piece to generate to generate that top dress, spring top dress script. Okay, so here's an example of how from nitrogen we could do identify an approach, an equation-based approach. So if we think about the wheat nitrogen recommendation, we've got yield goal times 2.4, which represents our total crop uptake needs for the wheat crop. That is not removal. That's just talking about how much total uptake that wheat crop is going to need. We've got our mineralization credit. We're saying on average, we expect to get 10 pounds of nitrogen for every percent of organic matter. Then we would subtract out profile in, and then if we had any previous crop adjustments, tillage, grazing, manure, all those other things that we can bring back in. So let's go through and think about, okay, what are each of these input variables that we need, and then determine, okay, do we have spatial data available to us, or do we have uniform data? And what can we use to build this variable rate script with? So if we think about yield goal, okay, if I've got historic yield monitor data for wheat, maybe I've got spatial data that I can feed in, spatially variable data. Soil organic matter, if I've got some grid sample or some zone data, I've got spatial data, or maybe I just have a field level composite, which would be uniform data. Same for profile nitrogen. And then typically our other adjustments, are all going to be uniform in nature. So this is an example. This is actually more of a Northeast Kansas example, but this is a field over in Marshall County that we worked up a variable rate nitrogen script on here several years ago. And so the producer had 3 years of wheat yield monitor history. So you can see here, wheat, the field was the wheat in 02, 06, and 05. And yeah, there's some variability, but there are some things that hold across years. In 02 and 06, this northern region of the field, consistently had some higher yields. This west central portion of the field tends to always be some of the lowest yielding. And then again, in 2 out of 3 years, the southern portion of the field tended to be higher yielding. If we work that together, we can work that together into kind of an overall yield goal layer that we could feed into that variable rate script. We also have grid sample data for soil organic matter, so we can feed that in. Again, it's 10 pounds per percent organic matter. Not a huge range here, but we go from a low of 2.6, which would translate into 26 pounds of mineralized in, up to a high of 3.5, which would be 35 pounds of mineralized in. So not a huge range, but hey, we got that data, so why not take advantage of it? So this layer on the left, this is our spatial yield goal layer we generated out of those 3 layers of wheat yield data. And so we would take this yield goal times 2.4. On the right-hand side was the spatial mineralized in estimate that we got from our grid sampled organic matter data. So we got this left-hand layer, yield goal times 2.4 would be our total uptake. And then we would subtract off this mineralized nitrogen layer on the right-hand side. We had previous crop adjustment of 0. Previous crop was soybean. A plus 20 pounds requirement for no-till would be the uniform things that we would put in there. And so as a result, we end up with this as a variable rate top dress script. So just kind of a step-by-step example of how a person could do that using a mix of both spatially variable as well as spatially uniform or field level type data. A few minutes about sensor technology. And so there's a lot of work done on this at K-State. You probably hear more about this coming out of Oklahoma. Frankly, it's a system that I feel is better suited to their production environment. We also have a couple, there are commercial service providers who are offering sensor-based management here in Kansas. Now, most of the time that's being done off of drones or satellite imagery. I think mostly satellite imagery, but there's different ways of getting at. Basically, the underlying idea here is that you can get a fairly decent estimate of final grain yield based on a sensor reading of greenness early on in the season. So Feeks 4 or 5, this would be basically right around joint, just showing this is a relationship from trials in Kansas looking at final wheat grain yield versus greenness at that growth stage. And so that's the overall idea. If we have a feel for what yield potential is this early, we could use this to drive a top dress script. So here's some data looking at sensor estimated yield versus actual yield. This is locations across Kansas, mostly eastern locations with the exception of Johnson down in southwest Kansas. You can see sensor yield versus actual yield, what the sensor recommendation was versus what the optimum was. And this was done from actually having actual nitrogen rate trials out in the field. And in this set of trials anyways, the sensor was doing a pretty decent job of hitting that. Once in a while though, we do have a miss, so Partridge in 2009, sensor recommended 25 pounds, the optimum was 60. So we were short 35 pounds in that example. And that often comes from, changes in late season yield potential. And so if we think about, so what can happen late season? Well, do we have an abnormally cool spring or abnormally hot spring for grain fill? Those are all things that can play with that on the late side. There's a number of handheld sensors available on the market that can be used for this. Oklahoma State has put out some good information looking at the use of nitrogen-rich strips, and I really like this approach. If you're going to go the sensor route, that gives you something to compare to. That also incorporates, mineralization, what's happening in the soil. But then you can say, okay, what's the non-nitrogen limited look like compared to where we have not yet fertilized? And so this can be done in the fall or the winter, ideally in the fall, going out and spreading some areas that will be, at a high enough rate that they're not nitrogen limited. And so, yeah, pre-plant, pre-emerge, look at it 30 days post and then prior to green up. And this is a really important point here is, if you're going to do this, you really need it in every field. If you've got drastically different productions, back to zones, soil types. And then the one I would really emphasize is cultivar, different varieties. And Jeannie and I looked at this a number of years ago where we went out and ran Green Seeker over the variety trials. And if you think about the varieties we have out on the market, we have a huge difference in terms of varieties that are very, very sprawled out in the early season growth versus varieties that are very erect and upright. And so if you've got different varieties on the farm, you really need to be treating those differently from a sensor-based management standpoint, treating each of those individually. Or if you've got a variety change in a field, if you got a field, that's split in half, planted to two different varieties, you really need to treat them as two separate fields from a sensor-based management standpoint, just because we know that plant architecture is going to be different. We've got some tools available on the K-State website. If you want to do this using some of the handheld type sensors, I would encourage you to check that out. Contact us if you got more questions on that. I think there's a role for using your historical yield monitor data. Go out and do the sensor-based stuff. If you got an area of the field that is consistently high yielding versus an area that is consistently low yielding, go out and do that sensor-based approach in each of those areas. Recognize and treat them differently. Recognize that we've got inherent differences in productivity in the field. Okay, with that, I've not left a lot of time for questions, but I'll hang around as long as people have questions to ask. And hopefully there was probably not comprehensive in nature, but hopefully we've given you a few things to think about.
Alrighty. Thank you, Lucas. Like I said, if anybody has any questions, you can put them in the Q&A box or in the chat box. Looks like we got one in the chat. If you variable rated lime to correct the soil pH, will it change your FOS map? And how soon should you resample?
Yeah, that's a great question, Jay. You know, that change is going to be, you know, somewhat slow. If we can detect it, you know, I think it would take a fairly large change in pH, you know, if we're going for something that really needs lime, you know, in the mid to high 4s and trying to bring that back to a 6. I mean, yeah, it is going to change that, but it's going to take some time. In terms of how soon should a person resample after that? Because we got a couple different pieces there, right? Because we know it's taking some time for that pH to actually work on the soil. And so, you know, there's going to be a lot of moving pieces there. Are we incorporating that lime? What's the ECC? You know, what's, you know, how, you know, if we're talking something that's pretty fine, we expect that reaction to happen a lot faster, right? As opposed to something that's fairly coarse. And so there's going to be a lot of variability there. Yeah. And I see in the comments, Marvin brought up a real good point. Yeah, that change is going to occur at the top of the profile long before the lower, right? Because with incorporation, now we're going to get more of that mixing, but if we're in a no-till liming situation, yes, we're going to expect that effect to start at the top of the soil surface and then work its way down. So I don't have a good answer for that, Jay. That's a real good question though, but yes, over time we would expect it to potentially change the FOS. The exception would be is if that FOS is just low soil test P to begin with, you know, pH alone, you know, may not free up enough to really change that. And it goes back to the buffering deal. We're going to see a lot less of a change in soil test P at lower soil test P levels, and we'll see a lot bigger change in soil test P at higher soil test P levels because it takes less to actually, it takes less change in FOS availability to move the needle because of the buffering.
Aaron, is there anything on YouTube question wise?
No, there is not.
Okay. Not see anything else on Zoom. So I guess
Yeah, so I guess the take home message is variable rate won't pay this year. I'm not sure it ever will. So if it's done right.
Okay, was there one more? Oh, yeah, I think there is one more question here that just turned up in the Q&A. How long to get a response from manure and no-till?
Yeah, I guess here, Martin, can you expand on that? Response to what? Response in terms of getting the FOS availability back? So, you know, and so I'll put a plug in here. You guys have the past videos posted. You guys had Peter on, what, 2-3 weeks ago, talking about the fertility value of manure application. And so I think that might be something Peter, I think probably covered in that talk, not to deflect, but just putting a plug in that these recordings from the past meetings are available. So.
Okay, great questions here. So if you have any more questions, just go on and put those in the Q&A or put those in the chat. And if we don't have time to answer it on here, we will certainly get those answered and to you. So again, my name is Sandra Wick. I'm the crop production agent for the Post-Rock Extension District. We just wanted to remind you, we'll have few little announcements here for bookkeeping. Be sure if you're getting credit for CCA, that you email your name and your number to Jeannie at jfalkjones@ksu.edu. And let me get this slide to advance. There we go. And again, we'd like to thank you for participating in our Crop Talk. I know you guys are really busy out there on the farm, and it's a pretty nice day out there today. No wind as of yet. But we really do appreciate you filling and completing the evaluations that we've had the first couple times. So we would like you to continue that. So here is the link to a survey or an evaluation for our presentation today and a QR code. So as you can see in the chat there, there's your link as well for that. So we really do appreciate it because it really does help us in future programming, not as, how we did today, but also maybe some future topics that we need to cover as well. And please join us next Monday. Our next one will be this coming Monday, February 21st, again, same time and location from noon to 1 p.m. Central Standard Time. Our next presentation will kind of continue the fertilizer questions and topic. So we're going to continue on with managing soil fertility during record high fertilizer prices. So that will be with Dr. Dorival Rios-Diaz. So please join us for that as well. So if this is the first time that you participated in our Crop Talk, you may mention or notice that some of the questions in our evaluation include some demographics for you. And even though you have done that before, if you would please continue to give us some demographics, because K-State is really wanting to know kind of our audience reach and where we are with that. There are some other meetings coming up, so I wanted to let you know, you should have noticed that in the slides that ran before our presentation started. This week we're doing our, excuse me, our North Central and Northwest K-State weed meetings. The first two start tomorrow, and then we have a couple on Wednesday as well. So the ones tomorrow are Colby is in the morning starting at 9 o'clock. In the afternoon will be Osborne. And then on Wednesday, Hill City the 16th at 9 o'clock in the morning, and Claflin that afternoon. So with that, I want to thank you for joining. If you missed the first two sessions, excuse me, those were recorded and put on the Northwest Agronomy events. So you can watch those as well. So without any further ado, thanks, and we will see you next week.